So welcome to everyone. So we are going to see the topic of design of footing. So in that footing, a structure is generally considered to have two main portion. So that one is superstructure and the other one is substructure. The substructure transmits the load of superstructure to the supporting soil is generally termed as foundation. The footing is the portion of the foundation which ultimately delivers the load of the soil and is thus contact with that the load of the superstructure is transmitted into the foundation or substructure through either column or walls. The object of the providing foundation to a structure is to distribute the load to the soil in such a way that the maximum pressure on the soil does not exceed its permissible bearing value, and at the same time the settlement is within the permissible limits. Foundation may be broadly classified under two heads. One is Sala foundation, another one is deep foundation. According to Tasahi of foundation, and then according to Tasagi foundation, a shallow of its depth is equal to or less than its width. In case of the deep foundation, the depth is greater than the width. Various types of shallow foundation. So first one is shrub footing. That is, it consists of wall footing and a single footing for square column and a single footing for circular column, sloped footing for column, and there is and spread footings. A spread footing or a simple footing is a type of shallow foundation used to transmit the load of an isolated column or that of a wall on subsoil. In the case of wall, the footing is continuous, while in case of the column, it is isolated. Next one is combined footing. A spread footing which supports two or more column is termed as a combined footing. Such a footing is provided when the individual footings are either very very near to the each other or overlap. Combined footings may be either rectangular or trapezoidal footing. These are the examples for combined rectangular footing. And next one is strap or cantilever footing. A strap footing consists of uh, uh, spread footing of two columns connected with strap wheel. The strap beam does not remain in contact with the soil and thus does not transfer any pressure to the soil. Such a footing is generally used to combine the footing of the outer column to the adjacent one of the one to the adjacents one of one so that the footing of the forms does not extend in the adjoining property. Next one is the star footing example and mat footing or raft foundation. A mat or raft is combined footing that covers the entire area beneath the structure and supports all the walls and columns. When the available soil pressure is low of building loads are heavy, the use of spread footing would cover more than one of the area, and it may prove more economical to use mat or raft foundation. These are the example of mat or raft foundation and pressure distribution of the foundation. Next, we have to see the combined footing. In this case, they are having two types. One is a rectangular footing, another one is a trapezoidal footing, and strap footing and the raft footing. This is the pictorial example of the all type of footings. So next we have to see the some problem. So first one is a square footing. A square footing supports a square column having size 2 meter by 2 meter. and the size of the column is 400 mm by 400 mm. The axial load applied on the column is 600 kilonewton. Determine one-way shear stress and two-way shear stress if effective depth is 400 mm. First, the length breadth of the beam is 2000 mm, and the depth of the footing is 400 mm, and acting a load of 600 kilonewton. So first, one-way shear. The formula is P soil equal to W divided by L into B into 600 into 2 into 2. So next, 150 kilonewton meter square. VXS P soil equal to L minus L divided by 2 minus of D into B. So two-way shear, net punching load, that is equal to W coil minus W soil reaction, and it is having a load of 504 kilonewton, and the punching shear is nothing but 0.394 newton per mm square. So the next problem is determine the thickness of the plain cement concrete footing to support an axial load 300 kilonewton. The size of the column is 25 centimeter by 25 centimeter, and the height of the footing is 1 meter by 1 meter, and use M20 grade of concrete. So next, first we have to find out the tan alpha value. Tan alpha equal to greater than or equal to 0.9 root of 100 into Q naught divided by FCK plus 1. So Q naught is nothing but W divided by LNTP, or say bearing capacity, which is lesser. Q naught equal to W is already given the load 300 into 10 power 3. This consists of converting Newton values, and L is nothing but 1000 and B is nothing but 1000. So finally Q naught equal to 0.3 Newton per mm square, and FCK is 20 Newton per mm square. So finally tan alpha greater than or equal to 0.9 into 100, and the Q naught value is 0.3, and the FCK is 20 plus 1, and tan alpha greater than or equal to 1.423, d by a greater than or equal to 1.423. So d divided by 0.375 greater than or equal to 1.423. So finally dl is 0.534 meter. And next problem is a square fitting supports a column 500 mm by 500 mm carrying a load of 600 kilonewton at an eccentricity of 75 mm. Determine the size of the footing. First one, if pressure is uniform at the base, and second one is pressure is not uniform at the base. Third condition is maximum bending moment in the case of uniform pressure, and fourth one is maximum bending moment in the case of not uniform pressure. Take SBC of the soil is 200 kilopascal. And so plain area equal to load by SBC of the soil. Load is nothing but 600 kilonewton plus 10 percentage of the weight is 10 by 100 into 600 divided by 20. This 10 percentage area is excess amount. So we consider the 10 percentage area in every footing. So L square is nothing but 3.3 meter square, and L is nothing but 1.8, say 1.9 meter. So projection at least A1 equal to 775 mm, and the right is 6225 meter. So next, the maximum bending moment in case of uniform pressure P64. The thickness of the minimum depth of the footing is 150 mm soil and 300 mm pile cap. So P soil is nothing but W divided by L into B. So load is 600 Newton, L is 1.9 and B is 1.9. That is equal to 1 P soil. Pressure of the soil is 166.2 kilonewton per meter square. And M max is nothing but F into Fx x bar 166.2 into 0.775 into 7.2 divided by 2 into 1.9. So Mx equal to 94.835 kilonewton. Non-uniform pressure, that is CG of the column, CG of the footing is same. Therefore, safe bearing capacity, that is FC plus FB. So Q naught equal to W dot T divided by A plus M by A into Y bar. So Q naught equal to W coil plus W into divided by L into B. M divided by L cube into B divided by 2 into L by 2. So to 200 greater than or equal to 600 plus 10 divided by 100 into 600 divided by L into L. So plus 600 into 75 divided by 1000 divided by L power 4 into 12 into L by 2. So L is nothing but 1.99 meter, say 2 meter, and P equal to W divided by L into P plus or equal to M divided by L power 4 divided by 12 and L by 2. So P equal to 600 divided by 2 into 2 plus or minus 600 into 75 by 1000, 2 power 4 divided by 2 into 2 by 2, and P equal to 183.75, 116.25 kilopascal. So next one is next problem is uh, next, and we have to find out the before the problem mu limit value. So that is equal to mu limit equal to 0.138 fck xu max d minus 0.42 xu max. So finally, the all the values are known value. Only the unknown value is depth. So we have to depth found 163.70 meters. Say 170 mm. These are the this problem shows the depth of the footing. And next problem is design a sloped square footing for a short column with the factor axial load 1500 Newton. SBC is 200 kilonewton per meter square, and use of M20 and Fe415. Size of column is 375 mm square. Unfactored load is 1500 by 1.5 which is equal to 1000 kilonewton. Minimum area of the footing required is 5 meters square, and adapt the square shape of the footing, that is size of the footing is 2.24. So provide 2.5 by 2.5 meter of footing, and q is nothing but 0.24 newton per mm square. Depth of the footing is nothing but 874.30 mm square. So we have to provide 900 mm overall depth of the footing. So next one is bending moment per meter width, that is equal to 647.24 kilonewton per meter. Next, the clear cover, and we have to find out the AST value, and finally provide the value is 12 mm dia at 110 mm center to center spacing. And after that, we have to find out one by one column depth of the value and the bond stress value. So all the values are found means we have to proceed another step. So finally, the bond stress value is nothing but 0.53 less than or equal to 1.2 1.28 megapascal. So once this function is satisfied, means we have to provide another function. Okay. So thank you. We will see in next video in other problems. Thank you.